Okay, welcome back. We're getting into it now. We're going to start talking about linear optimization and some ideas about the geometry of linear optimization. In particular, develop ideas about polytopes and polyhedra. So we have already been talking about the importance of linear programming, and the idea for linear programming is that it is convex on the one hand, so we can leverage all of the tools of convexity, in particular duality, and at the same time, optimal solutions at extreme points or corners. We're going to define this, all of these things. You can just think about this as extreme point as corners, which have the power to encode combinatorial structure. And that is the whole power here of linear programming. And again, you know, our picture here is this. And so we have our extreme points. So let's start with the basic objects that we're interested in. Everything that we do is going to be in n dimensions. There is extensions of linear programming to infinite dimensions. This is not going to be of immediate interest to us. But you know, as a side note, those of you that have taken a course in combinatorial in convex optimization, you know that a defining characteristic of a convex set is that it is equal to the intersection of all half spaces that contain it. And in particular, that means that any convex optimization problem can be written as a linear optimization problem if you have the patience to write out all potentially infinitely many constraints. For us, we're not going to be focused on that. We're in n dimensions. So some basic definitions that we need. A hyperplane, sometimes called a codimension 1 affine subspace, is something of the form X, all X in Rn, such that A transpose X equals B. This is codimension 1 because I have one equality constraint, therefore I have n-1 degrees of freedom. Codimension 1 just allows us to say that without specifying what n is. So this is called a hyperplane. A half space, which we could denote by H plus or H minus, is X in Rn such that A transpose X is greater than or less than or equal to B. And the intersection of hyperplanes and half spaces is what's called the polyhedron, which I'll denote by P. And capital A, I can't really do boldface here, so A is an m by n matrix. That means, and B of course is just matches dimensions. So in this case, it's an Rm. This is an intersection of m half spaces. Basically, what we've been drawing, and it's easy to show that these are all convex. So you know we're getting warmed up here. So why don't we just show that it's an immediate consequence of the linearity involved in the description of this. So just for practice here, let's suppose x1 and x2 is in P, and let's take x3 equal to lambda x1 plus 1 minus lambda x2, where lambda is something in 0, 1. Then we can check that x3 is in P. That means that ax3 is greater than B. And again, this is really just by linearity. ax3 is equal to lambda ax1 plus 1 minus lambda ax2. And this is component-wise greater than or equal to lambda b plus 1 minus lambda b, which is B. Hence, x3 is in P. And a note that that H and H plus, the way I wrote them, are just special cases of P. We can get equality constraints just by flipping signs, having AX less than B, sorry, AX greater than B, and minus AX greater than minus B. That's equivalent to the equality. Okay, now let's go back to this fundamental picture that I've been drawing. And what we care about here are the corner points, which we can see by the picture. So we need to define this. The main result is that the following three definitions that I'm going to write are equivalent. So let's just, even because it's important, write it this way. Some shorthand that you often see all over the place, TFAE. The following are equivalent. And they're definitions. So maybe I should add a D here, but TFAE. The following definitions are equivalent. And what I'm defining is I'm going to use EXT for extreme points of P. I'm going to use that in all three definitions because believing the statement of the theorem that all three definitions are equivalent. So X is an extreme point of P if I cannot write X as the convex combination of two distinct points in P. And you can see that that's true about the corner. So again, let's just write this definition out. If there does not exist a Y that's different from Z, where both of these are elements of P, and X is equal to lambda Y plus 1 minus lambda Z, where lambda is in the open interval 0, 1. That's really just saying that also X is neither Y nor Z. Again, you can just draw this out by picture. Always a good exercise for you to translate anything from algebraic expression to a geometric expression. Second definition, X is an extreme point of P if there exists a vector C in the same dimension as X, in the same dimension as a polytope, such that C transpose X is strictly less than C transpose Y for any Y that's in P but different from X. This is an optimization characterization of extreme points. In other words, there exists some linear optimization objective so that X is the optimal value, is strictly less than any other value that's feasible. And finally, something that's going to be extremely useful for us is a linear algebraic characterization, and it basically says, again in pictures here, you have a shape in two dimensions like that one I've drawn on the upper left. What is a corner? It's something that is the intersection of two of the lines. Two lines in two dimensions. In n dimensions, we're going to need n lines. So the third definition is X is an extreme point of a polytope P if n at least n of the constraints are independent and there's a bunch of words that mean the same thing. Tight, binding, active. So embedded in here are two definitions. What does it mean for two constraints to be independent? It just means that their A vectors are independent. So constraints are independent if the collection of vectors AI that define each of those constraints are independent. So this collection AI is independent as vectors in Rn. And then tight, binding, or active just means that the constraints are satisfied with equality. So this means AI transpose X is equal to BI. And of course, in all of this, I maybe didn't write it explicitly, but X is an extreme point if it is also feasible. So this last constraint also has another very common name in the linear programming literature. It's called a basic feasible. Oops. It's called a basic feasible solution. And the main result is that these three definitions are equivalent. Okay, so there are many equivalent ways to represent a polytope. We've been so far talking about AX less than B, but it's going to be very useful, especially when we're talking about an algorithm simplex method for solving linear optimization problems, to represent all of our polytopes, polyhedra, in a canonical way. I've said polytopes and polyhedra, so I should just make, could have been better organized, but let me just make this small note here. If P is bounded, it is called a polytope. Okay, so a standard form polytope is of the form AX equal B, X greater than or equal to 0. And anything of this form, of course, with a different A and B, can be brought into the form AX equals B, X non-negative. So again, let's just very quickly do that exercise. So if I have AX, I guess I had greater than or equal to B, but it doesn't matter. We could have switched that with a sign. AX is less than or equal to B. I can introduce additional variables and write AX plus identity times S is equal to B, where now S is greater than or equal to 0. So you can see that this is equivalent in the sense that if a particular value X satisfies AX less than B, if and only if there exists a non-negative S, vector S, so that AX plus I identity times S is equal to B. And then the final little detail is just to make sure that X is non-negative. We can use a standard trick in linear optimization of just writing any scalar X is equal to its positive part minus its negative part, where xi plus and xi minus are greater than or equal to 0. So finally, we can write this as ax plus minus ax minus plus identity times s is equal to b, and x plus, x minus, and s are all greater than or equal to 0. So you see that what a and b are maybe different. Actually, not b in this case, but a has changed. But I can write anything in what we're going to call standard form. And we're also going to assume, without loss of generality, that whenever I write something in standard form, a polytope of this form, I'm going to assume that the rows of A are independent. Okay. Okay, so now let's go back to extreme points and see what do they look like. What are the extreme points of something that's in standard form? So our polytope P is equal to AX equals B, X non-negative. And we're going to use the third definition. We need, so X is an extreme point if we have, this is a subset of Rn. That means that A is an M by N matrix. M by n, and m is going to be less than or equal to n by our independence assumption. And by the way, if it's equal to n, this is not a very exciting polytope. It's just a polytope with one point. So x is an extreme point if we have n tight and independent constraints. So let's see where we're going to get them. M come for free. They come from ax equals b. If a point is feasible, it by definition has to satisfy ax equals b. But therefore, we also need n minus m more. Where are these going to come from? These come from x greater than or equal to 0. So that means that an extreme point of a polytope expressed in canonical form must have at least n minus m values set to 0. N minus m of these must be satisfied with equality. So that means that if x is an extreme point, by rearranging the coefficients, I can write it as follows. So let's let b equal the coefficients. So this is a subset of 1 to m. Be the indices of xi of x. You can do better. The indices of x that are possibly non-zero. They still might be 0, but they are not in the collection of n minus m that must be 0. So b is the other ones, the ones that I'm not enforcing to be 0. So the indices of x that are possibly non-zero. All the others are 0. So by some abusive notation, what does that mean? It means that x I can write as x subscript b and 0. So what x subscript b means is just those indices of x. And just for convenience, I'm just writing them as if they were the first m of them. But now we also know what xb is because I need to satisfy ax equals b. But what does that read? Again, by the same abusive notation, let me reorder the columns so that I have the columns corresponding to b. I'll write it like that. A, b come first, and then the remaining columns times xb and xb complement. We already said that those have got to be 0. This is equal to b. And you can just see that this immediately tells us that xb is equal to a b inverse times b. Okay, so this tells us that if you want to find an extreme point of a polytope in standard form, you pick m of its coordinates. That gets you m of the columns of a. That's ab. And you set all of the entries of x that are not in b, not in the index set b. We're also going to call b a basis, but not in the index set b. Set those equal to 0, and the rest you set equal to ab inverse times b. And if ab inverse times b happens to be non-negative, then you found a corner point. So now we know what extreme points look like of something in standard form. And by the way, a corollary of this, in fact, a corollary of the theorem that those three definitions are equivalent, is that we have to have a finite number of extreme points. Maybe that's obvious, or we're lured into thinking that that's obvious just by thinking about the picture. But it's nice that we get it so immediately from this characterization. And this again tells us, this gets us closer to this idea that the corners really are encoding combinatorial information. Because what does this story on this slide tell us? It tells us that you choose a subset of m of the columns of A, and that corresponds to an extreme point. Again, to be precise, it corresponds to an extreme point if AB inverse B is greater than or equal to 0. So it really is an N choose M type of story here. It really showcases the combinatorial flavor. Okay, let's keep going. Now, when we have a polytope, one downside of standard form is that it is really difficult to draw anything in standard form. The best I can do is with M is equal to 1. You can draw the face of the simplex. So I'm going to go back and forth. It's easier for me to write many inequalities when we're not in standard form. So when we have a shape that's not in standard form, or hey, I can do that. Let's draw the one shape that I can draw that's in standard form. And so this shape here is of the form A transpose X equals 1, X non-negative in 3 dimensions. So with either one of these, well, this is not so good because there are just 3 extreme points, so they're all adjacent. So let's go back to the first one. So you see that these 2 points that I've circled are neighbors. They're adjacent, whereas this other point is non-adjacent. So easy enough to see from a picture. I want to understand algebraically what this means. And the picture kind of tells the story. So what do these have here? These two, this extreme point and this extreme point, they have a common binding constraint, namely this. Whereas if I look at this extreme point and this extreme point, they don't share any extreme point. So let's just translate this into the algebraic view. So I have my polytope in standard form, ax greater than b, x non-negative. An extreme point is of the form x is equal to x, b, and 0, where b has size m and is a subset of the indices from 1 to m. So as I mentioned before, b is sometimes called a basis. And as you can see, the minute and again, why we call the corners combinatorial is that even though this is a continuous object and the values of the corners could don't necessarily have to be 0, 1 or whatever, they do have to be rational if the coefficients a and b are rational. But as soon as you choose the basis, you are led to what the extreme point must be. So again, the extreme points really are in one-to-one correspondence with subsets of size m. So I have a basis like this. So a neighboring extreme point, borrowing the intuition from the picture on the previous page, we need to find an adjacent basis. A basis b1 and b2 are adjacent if they share m minus 1 indices. So that means that the 2 corresponding extreme points, again, once you specify b1, you've got x1 that's equal to, I'm abusing notation here, and x2 is xb2, 0. I'm abusing notation because b1 and b2 will not both be the first m elements, but it's too cumbersome to really write it out in another way at this point. And so this is what I mean. So one question for you is how many neighbors or adjacent vertices, neighbors, can an extreme point have? We can think about that. So this tells us what an extreme what are the neighbors of extreme points? One important other point, which again is very clear from drawings, is this concept of a convex hull of extreme points. So let me just give the quick definition. So given points x1 to xn, the convex hull, sometimes denoted by just conv or sometimes ch of x1 to xn, is all points x that are equal to sum of lambda I. Let me make this a d, so we're not thinking about n being the dimension. Sum of lambda I xi, I equals 1 to d, where lambda are non-negative, and sum of lambda I is equal to 1. So an important result, again, immediate from the picture, is that for any polytope, so if P is AX less than B and it's bounded, then, in fact, whether we specify the extreme points or the inequalities that carve it out, we have the same object. So P is equal to the convex hull of the extreme points of P. Again, this seems obvious, but it has deep connections to Banach space theory, where understanding the relationship between extreme points of sets in a Banach space is really important. But again, none of that, we don't need to deal with any of that here for what we care about. So let's just wrap up this this lecture or this segment by going back to this idea of optimality and extreme points. So let's bring in an objective function, minimize C transpose X, subject to X in a polytope. So X in P and X and P is bounded. I don't even care if it's in standard form or whatever. Then a basic result is something that I've mentioned a number of times, that this optimization problem, again, if it's feasible, meaning if P is non-empty, then there exists an optimal solution at an extreme point. And this is essentially an immediate consequence at this point of what we said on the previous slide. So it follows from the previous slide, because if y is optimal, if y is in P, then it means that y is equal to some convex combination of zi's, where zi's are extreme points. And then by linearity, C transpose y is a convex combination of C transpose zi. And if you're an average of things, you really can't be better than every single thing in the average. So there's got to be something in zi, one of these zi's that's at least as good as you, if not better. All right, we're going to stop here, and we're going to pick this up in the next lecture.